Hello and welcome. In this comprehensive lesson, we'll dive into two fundamental and powerful tools in biostatistics: confidence intervals and chi-square tests. By the end of this video, you will be able to calculate and interpret confidence intervals for means using the t-distribution, and you will be able to perform and interpret a chi-square test for independence. These methods are essential for drawing meaningful conclusions from data in biological and medical research. Let's get started. First, let's tackle confidence intervals. Imagine you're studying a population, like all patients with a certain disease, and you want to know a specific characteristic, like their average blood pressure. It's usually impossible to measure everyone in the population. So, what do? We take a sample. From this sample, we can calculate a sample mean, which is our best guess, or point estimate, for the true population mean. But how accurate is this guess? A confidence interval provides a range of values that is likely to contain the true population mean. It's a way to quantify the uncertainty in our estimate. Think of it as a net you cast to catch a fish. The net isn't a single point, it's a range. A confidence interval is that net for the population mean. The formula for a confidence interval for a mean is the sample mean, plus or minus a margin of error. This margin of error is what creates our range. The margin of error depends on three things: the variability in the data, the size of our sample, and our chosen confidence level. Let's explore that last one next. The confidence level is a crucial concept. It's the probability that our confidence interval will contain the true population mean. Commonly used confidence levels are 90%, 95%, and 99%. Let's break down what a 95% confidence level really means. It does not mean there's a 95% chance the true mean is in this specific interval we just calculated. Instead, it means that if we were to repeat our sampling process many times, 95% of the confidence intervals we construct would contain the true population mean. So it's a statement about the reliability of our method, not about a single interval. A higher confidence level, like 99%, gives us more certainty, but it also results in a wider interval, which is less precise. It's a trade-off between certainty and precision. Now let's talk about the distribution we use. When the population standard deviation is known, we use the z-distribution. But in biostatistics, we rarely know the population standard deviation. Instead, we have to estimate it using the sample standard deviation. When we do this, we introduce more uncertainty, and the appropriate distribution to use is the t-distribution. The t-distribution is similar to the z-distribution, but it's wider and has heavier tails. This accounts for the extra uncertainty from estimating the standard deviation. The shape of the t-distribution depends on a parameter called degrees of freedom, which is simply the sample size minus 1. As the sample size gets larger, the t-distribution gets closer and closer to the z-distribution. So to recap, when we're estimating a population mean from a sample and we don't know the population standard deviation, we use the t-distribution. This is a very common scenario in biostatistics. Let's put it all together. Here is the formula for a confidence interval for a mean using the t-distribution. The formula is the sample mean, x bar, plus or minus the t-critical value, t star, multiplied by the standard error of the mean, which is the sample standard deviation, s, divided by the square root of the sample size, n. Let's break down each part. X bar is our point estimate. S over the square root of n is the standard error, which measures the variability of our sample mean. The t-critical value, t star, is the multiplier that determines the width of our interval. It depends on the confidence level and the degrees of freedom, which is n-1. To find t star, we typically use a t-distribution table, or statistical software. You'll need to know the degrees of freedom and the alpha level, which is 1 minus the confidence level. For a 95% confidence interval, alpha is 0.05, and we look for the t-value that leaves 0.025 in each tail. Let's work through our first example. Suppose we measure the systolic blood pressure of 15 patients. We find the sample mean is 120 millimeters of mercury, and the sample standard deviation is 10 millimeters of mercury. We want to calculate a 95% confidence interval for the true mean systolic blood pressure of the population. First, we need the degrees of freedom, that's n-1, so 15 minus 1 equals 14. Next, we find the t-critical value. For a 95% confidence interval with 14 degrees of freedom, The t-star value is 2.145. Now we can plug everything into our formula. The interval is 120 plus or minus 2.145 times the quantity 10 divided by the square root of 15. Calculating the standard error, we get 10 divided by 3.873, which is about 2.582. Multiplying by t-star, our margin of error is 5.536. So, the 95% confidence interval is 114.464 to 125.536 millimeters of mercury. How do we interpret this? We are 95% confident that the true mean systolic blood pressure for the population of patients is between 114.464 and 125.536 millimeters of mercury. Let's see how the confidence level affects the interval. Using the same data, let's calculate a 90% and a 99% confidence interval. Remember, our sample mean is 120, standard deviation is 10, and sample size is 15. The degrees of freedom are still 14. For a 90% confidence interval, the t-critical value with 14 degrees of freedom is 1.761. Plugging this in, we get 120 plus or minus 1.761 times 2.582, which gives us a margin of error of 4.547. The 90% interval is 115.453 to 124.547. Notice it's narrower than our 95% interval. Less certainty, more precision. Now for a 99% confidence interval, the t-critical value is 2.977. The calculation gives us 120 plus or minus 2.977 times 2.582 for a margin of error of 7.693. The 99% interval is 112.307 to 127.693. This is the widest interval. More certainty, less precision. This demonstrates the fundamental trade-off between confidence and precision. Let's try another example. A study measures the reaction time of 25 participants to a visual stimulus. The sample mean reaction time is 250 milliseconds, with a standard deviation of 40 milliseconds. We want to find a 95% confidence interval for the true mean reaction time. First, degrees of freedom. 25 minus 1 is 24. For a 95% confidence interval with 24 degrees of freedom, the t-critical value is 2.064. Now, let's calculate the standard error. The standard error is 40 divided by the square root of 25, which is 40 divided by 5, giving us 8. Next, the margin of error. The margin of error is 2.064 times 8, which is 16.512. Finally, the confidence interval. The interval is 250 plus or minus 16.512, which is 233.488 to 266.512 milliseconds. We are 95% confident that the true mean reaction time for the population is between 233.488 and 266.512 milliseconds. Let's move on to our second major topic, the chi-square test for independence. This test is used to determine if there is a statistically significant relationship between two categorical variables. For example, we might want to know if there's a relationship between smoking status and the development of lung cancer, or between a new drug and the improvement of a condition. The core idea is to compare what we actually observe in our data to what we would expect to see if there were no relationship between the variables. This comparison is done using a contingency table, which displays the frequencies of each combination of categories. The test statistic, called the chi-square statistic, quantifies the difference between these observed and expected frequencies. A large chi-square value suggests a large difference, and therefore, a relationship. Let's walk through the steps of a chi-square test for independence. First, we state our hypotheses. The null hypothesis, H0, is that the two variables are independent. The alternative hypothesis, HA, is that they are not independent. Second, we calculate the expected frequencies for each cell in our contingency table. This is what we'd expect if the null hypothesis were true. Third, we calculate the chi-square test statistic using this formula. We sum the squared difference between the observed and expected frequencies divided by the expected frequency for every cell. Fourth, we find the critical value from a chi-square distribution table This value depends on our chosen significance level, alpha, and the degrees of freedom, which is the number of rows minus 1, times the number of columns minus 1. Finally, we make a decision. If our calculated chi-square statistic is greater than the critical value, we reject the null hypothesis and conclude there's a relationship. Otherwise, we fail to reject the null. Let's work through an example. A study investigates the relationship between smoking status and the development of a chronic cough. Here is our contingency table. We have 100 smokers and 100 non-smokers. Among smokers, 40 have a cough and 60 do not. Among non-smokers, 10 have a cough and 90 do not. Step 1. Hypotheses. H0 is that smoking status and cough are independent. HA is that they are not independent. Step 2. Calculate expected frequencies. For the smoker and cough cell, the expected frequency is the row total 100 times the column total 50, divided by the grand total 200, which equals 25. We do this for all 4 cells. The expected frequencies are 25, 75, 25, and 75. Step 3. Calculate the chi-square statistic. We sum the observed minus expected squared divided by expected for each cell. This gives us 9 plus 3 plus 9 plus 3 for a total chi-square statistic of 24. Step 4. Find the critical value. Degrees of freedom are 2 to 1 times 2 to 1, which is 1. For a significance level of 0.05, the critical value is 3.841. Step 5. Make a decision. Our calculated chi-square of 24 is much larger than the critical value of 3.841. Therefore, we reject the null hypothesis. Conclusion. There is a statistically significant relationship between smoking status and the development of a chronic cough. Let's try a practice question for confidence intervals. Take a moment to pause the video and work through it yourself. A study measures the cholesterol levels of 30 patients. The sample mean is 200 milligrams per deciliter, and the sample standard deviation is 25 milligrams per deciliter. Calculate a 99% confidence interval for the true mean cholesterol level. All right, let's go through the solution. First, degrees of freedom are 30 minus 1, which is 29. For a 99% confidence interval with 29 degrees of freedom, the t-critical value is 2.756. The standard error is 25 divided by the square root of 30, which is about 4.564. The margin of error is 2.756 times 4.564, which is 12.579. The confidence interval is 200 plus or minus 12.579, giving us a range of 187.421 to 212.579 milligrams per deciliter. So, we are 99% confident that the true mean cholesterol level for the population is between 187.421 and 212.579 milligrams per deciliter. Here's a practice question for the chi-square test. Again, pause the video and try it on your own. A study investigates if there's a relationship between gender and preference for a new drug versus a standard treatment. Here is the observed data. Is there a significant relationship at a 0.05 significance level? Let's solve it. Step 1. Hypotheses. H0 is that gender and treatment preference are independent. HA is that they are not. Step 2. Expected frequencies. For the male and new drug cell, it's 50 times 50 divided by 100, which is 25. In this case, all 4 expected frequencies are 25. Step 3. Chi-square statistic. We calculate the sum of observed minus expected squared divided by expected. This gives us 10, 10, 10, and 10 for a total chi-square of 40. Step 4. Critical value. Degrees of freedom are 2 to 1 times 2 to 1, which is 1. For a 0.05 significance level, the critical value is 3.841. Step 5. Decision. Our calculated chi-square of 4 is greater than the critical value of 3.841. We reject the null hypothesis. Conclusion. There is a statistically significant relationship between gender and treatment preference. Let's quickly recap what we've covered. We started with confidence intervals, which provide a range of plausible values for a population mean. We learned that when the population standard deviation is unknown, we use the t-distribution. and we saw how the confidence level affects the width of the interval. Then, we moved on to the chi-square test for independence. This test helps us determine if two categorical variables are related by comparing observed frequencies to expected frequencies. A large chi-square statistic indicates a significant relationship. You are now equipped to calculate and interpret these essential biostatistical measures. Thank you for watching.